Hello, students. We are in the heart of Chapter 8, and the section of reactions we're covering today includes reduction reactions, specifically hydrogenation and oxidation. So when we get to the section about oxidation, pay very careful attention to stereochemistry and the reagents you need to use to get the desired stereochemical outcome. Specifically, we're going to be looking at epoxidation and hydroxylation, sometimes dihydroxylation it's called, and then we're going to be able to cleave alkenes to carbonyl compounds. But first, we start with hydrogenation. So hydrogenation, excuse me, you already had a bit of a preview of this. You're adding HH or hydrogen, the molecule, across the double bond. So you can take an unsaturated compound and make it saturated. This can work really well, mainly when you use a metal catalyst. So normally if you just pump in a bunch of hydrogen gas, it could take a while for this reaction to occur, but if you can add a catalyst like platinum or palladium, you can affect this more swiftly. And to let you know, you end up adding the hydrogens across the same face of the alkene. If you can get a product that is chiral, then you'll get addition from both the top and bottom faces. So if you added from the top here, that would have meant the hydrogens are up and then these groups are down. If you added from the bottom underneath, your resulting compound would look like this with the ethyl and methyl up. Okay, a little bit on the catalyst. The catalyst is going to help lower the activation energy. So normally you might have a big hill to climb to reach the transition state, but with a catalyst, you lower that. You're making the reaction easier. So this is very common in a lot of biochemical processes. We can do this in the lab. How does that work for catalytic hydrogenation? The metal here are these balls representing atoms of the metal. And the reason why this helps the reaction go faster or lower the activation energy is it makes it easier to reach the transition state. Here, you already have the hydrogen attached to the metal surface, and the metal surface can also pre-coordinate the alkene. It can break this alkene double bond and affix one part of the carbon to the metal, and then you can deliver one and then eventually two hydrogens. So overall, a catalyst is very commonly used to carry out this reaction. Just some common ones, you don't need to know these specifically, but there are just some common ones that you can use. So rhodium with some sort of ligand, this is a phosphine ligand, and chlorine, this is called Wilkinson's catalyst. These are really useful because these groups here can dissociate and the alkene can attach to it in its place. There are some other ones. One, there's the homogeneous category where they're soluble in the reaction medium, or heterogeneous. So you would see them floating around, like visually, you'll see a physical metal floating around. This is when you use platinum, palladium, or nickel, and these are insoluble in the reaction mixture. And I just want to show common ones in case you are doing research in a lab. Palladium on carbon is a very popular one to go towards. This is powdered palladium supported on a charcoal surface, the carbon surface, or platinum oxide here, platinum 4 oxide, Adams catalyst. The really, really cool thing about this is scientists have been able to do this so that you can get enantioselectivity, meaning if the resulting compound is chiral, generally you would get hydrogen adding from the top or bottom face, but which would result in a racemic mixture, but you can actually have one of these ligands attached to the ruthenium in this case as your metal, and this component, this particular ligand, can be chiral itself. So this is chiral, and so when the alkene adds to it, it's adding in a chiral environment and giving, in this case, 95% enantiomeric excess, meaning you have that much percent excess of one enantiomer over the other. So let's just practice. You guys are in the business of synthesizing compounds now. So if I give you a substrate and a set of reagents or conditions, you should be able to produce the product. Pay attention to stereochemistry. So pause and write out the products for these and then unpause. So for the first one, I'm going to add, excuse me, hydrogen to the top or bottom. The two hydrogens are on the same face. What that effectively does is if I add hydrogen on the top, this methyl group then is down. And then the other carbon I added to is not a stereocenter because there are now two H's. Notice the upper methyl is fixed up in both. I could also add the hydrogen from the bottom face, and then that would push that methyl up. So in this particular case, you get diastereomers, since there's a fixed chiral center up top, and then it varies on the second lower one. Okay, this guy with the nickel, as long as you have hydrogen in one of the metals, you can affect hydrogenation. And what you get out is a compound with a single chiral center. Hydrogen can add from the top, wedged, or from the bottom, dashed. And since there's only one chiral center, this ends up being enantiomers. Our next category is oxidation. So you're going to be adding OH across the double bond, but two of them. So we call that a dihydroxylation. So you could take this ethylene, get ethylene glycol, which is a diol, D-I-O-L, diol for two alcohols. So what's really powerful in this section is depending on the reagents you use, you could take an alkene and get the diol product, the dihydroxylation product, where one OH is up and the other is down. You get the anti-product. And this is where we're adding on a cyclic alkene. Or you could get the syn product here, both up or both down. So I'm going to go over the anti-dihydroxylation first. It's a two-step process. First step is you add a peroxide to create an epoxide. You can isolate these. These are actually found in some drug products. And then in step two, you add an acid. You can just write H3O plus, and that ends up helping you open up the ring to give this diol. And this is similar to opening up a bromonium ion, if you recall, where you end up getting the anti-product. In this case, we do have no preference to add from one or the other side to open up the ring, so you do get the enantiomer. Okay, here are peroxides. This is a peroxy acid, and you can have a simple one here with just an acetyl group, or this one here with a chloro off a benzoyl group. And so we call this metachloroperoxybenzoic acid, or MCPBA for short. So these are very useful. I don't need you to know the mechanism, but basically the alkene adds into the O, and then a lone pair or a bond can transfer to generate the three-membered coordinate. This is a transition state. Eventually, you generate your epoxide. So the O here, the second O attached to the H, is the one that's added as the epoxide. I don't need you to know this mechanism. I won't test you on this, but you can see how this is happening. And then you're left over with a byproduct of that reagent. Okay, the more substituted your alkene, the faster the rate of the reaction. The reason is they're more nucleophilic. They're going to add that O a lot faster. You do need to know this mechanism. Starting from the epoxide, your second step to open up that ring is to add an acid. So you protonate the O to get OH+. So you add the H and kick out water in this case. Then this is souped up. So just to let you know, the epoxide is reasonably stable. You do have some ring strain, but still, it's not going to just open it up on its own. So you're trying to soup it up by opening it up, by protonating it and then opening it up with water. You have equal probability to open on either side. That's why we get enantiomers at the end. But look at what happens. You add water from the bottom. This is a backside attack. We call this SN2 again. You've seen this before. And that pops open the ring. So if the ring is up, you attack from the bottom. That means this water part is down, bottom. And the ring just pops open. It's pointed up, so it's still up. That's why we get the anti-configuration at the end. Remember, there's one final proton transfer step. We've seen this before. Anytime you add water, you have this extra H hanging off, and O has a formal plus charge. So use a second water and just pick off that H, and the lone pair goes on to O, and you get your diol product. Plus, it's an enantiomer. Again, this is similar to opening up the ring of a bromonium ion or mercurinium ion. So if you recall, you develop a partial positive charge at the more substituted center. We didn't have that situation in this case, but if you have an asymmetric alkene, open up the ring so one of the diols adds in to the more substituted center. Okay, you guys predict the product for this. What you get, because you're doing two steps, MCPBA first to generate the epoxide, and then you're going to add water to open up the ring. So water will add in at the center, but you can generate the epoxide on the top or bottom face, and you'll add and open up the ring here. So you'll kick open so that this OH will be on the top or the bottom, and then the other OH is anti to that. That means if this OH is down, the original methyl here is pointed up. If this OH is up, it opened it up from the top, then that methyl is down. So just notice that the OHs are anti in both structures. Just study this. Study that you have this alkene and the methyl group is preserved in both products, but just notice the OHs are anti, and you do get the opposite configurations here. Okay, now let's look at the second type, the Syndihydroxylation. That means you can take the cyclic alkene, generate OH and OH, but they're on the same face, both up. Just to let you know, both down exist, but it's the same molecule. If you flip this over, it's meso. So this is a reagent that can affect that, osmium tetrachloride. And here we have sodium bisulfite. You can use a couple other things though. Your first step is just adding the osmium to form this osmate ester. I don't need you to be able to show me how to do this. And then this guy can be, you can release the osmium by adding sodium sulfite or sodium bisulfite and water to give the diol. You do have those two steps. So I do need to see number 1 and number 2. But osmium tetraoxide, it's expensive, it's toxic. So one way we can reduce that issue is to add just catalytic osmium and some sort of oxidant to reoxidize it. You can use and methylmorpholine oxide, NMO. You could just write NMO. Or you can add this peroxy acid, the terabutyl peroxy acid. Both of these would give you the same product in reasonable yields, and in some cases, very good yields. So let's practice this. You are going to predict the product for these. The first one I've got osmium tetroxide catalytic with NMO, and then I want you to give me the substrate and the reagents to make this epoxide and these two epoxides. Okay, pause, take your time, and then unpause when you're ready. So for the first one, I'm going to get the syndiol. So to reflect that, I keep the parent skeletal system the same. 1, 2, 3, 4 butane here, but then I put the OHs both up on top. That's syn. So that's what you get from this combo with osmium tetroxide and NMO. How to make this? How did I show you how to make an epoxide? You only use MCPBA. So notice I omitted the second step too with the acid, because that would have opened up the epoxide and led to the diol product. So just do MCPBA. And I have this, the methyl syn. So that has to come from the cis alkene, because the epoxide is just formed by adding an O on one side. So you would just add O on one side here, and then the methyls are syn. It's only when you open up the epoxide do you do backside attack, open up the ring to get the anti-product. In the second case, I got methyl up and down and both enantiomers. Both enantiomers. So I had to have started from the trans product. So you can envision this as an oxygen adding from the top. And if you're looking at a side view, you see a methyl back or forward or back. So you would add the O from the top or the bottom. Okay, our final oxidation reaction is really, really cool and fun. You can split an alkene in half and generate the carbonyl compounds. So look at what I'm doing. I have this alkene here. It's asymmetric. It's got two methyls on one carbon and then this propyl chain on the other, but I can cleave it right through the center. And instead of the alkene bond, you add two O's. So I maintain this 1, 2, 3 carbons, but now I have a double bond O, and where I had a double bond C, I now have a double bond O. So the way that you do this is you add ozone and dimethyl sulfide, DMS. You could just write this. This is two separate steps, ozone and DMS, and you could get your products. So generally, this would, if you only have one group, that gives you the aldehyde. There's an H here. If you do it under potassium permanganate and acid, instead of the aldehyde, you can oxidize the aldehyde up to the carboxylic acid. So if I started with this alkene, I could cleave down the center. So instead of the C double bond to C, I have C double bond to O on this left side for the ring. And on the right side, I have C double bond to O, but instead of the H, I have OH. And then the other part is ethyl. Okay, this can kind of be a little bit of a puzzle sometimes. So just be open to moving around, rearranging compounds to help you visualize things. I'm going to show you the mechanism, but I'm not going to test you on this. This is ozone here. You're going to generate in this cycloaddition a 5-membered intermediate called the ozonide. And this can fragment to give you these two, this ketone and this other intermediate, which can further add to each other and generate this modified ozonide. The other thing is at the very end, you'll use your DMS or possibly zinc and acid or potassium permanganate and acid. And then finally, just cleave and you'll generate your carbonyl from this side and your carbonyl from this side here. Okay, this is our final slide here. You guys are going to predict the products. I have ozone and dimethyl sulfide in both cases. When I give you the starting alkene, you give me the product. The other, I give you the product, you give me the starting alkene. Pause and unpause when you're ready. So this first one, what we have to do is cleave at 2 places. I numbered this because it can be hard to track. I'm just numbering 1, 2, 3, 4, 5, 6, 7, 8 around the ring. So I'm going to cleave it here. That opens this up. Instead of the double bond to carbon, I have a double bond to O at carbon 2 and a double bond to O, your carbonyl, at carbon 7. What about the rest of the ring? It's untouched except here at this alkene, I cleave it right through here. So at carbon 4, I have another double bond to O, and this fragments away. It's still in the reaction mixture. I'm just saying it's away from this bigger group. So I have a carbon double bond to O, and I have an aldehyde and a methyl, which is this here. So you can leave it like that, but it's nicer to open it up, and you can see you have this chain, 8-carbon chain with a carbonyl at the 2, 4, and 7 position. And you have this ethanaldehyde product. This one may be a little tricky, but what you could see is I start with a C10 compound and I end up with a C5. That means I am showing all the products, so I must have had 2 of these. I must have cleaved here, so you would combine 2 of these together, and instead of the O, put your CC double bond. You're not always going to have the situation where you cleave and they're identical. Sometimes you'll have this, where you cleave and you get a separate product that's different. So just be mindful of that when you practice this. All right, I'm going to end here, and we'll continue with our last part on cyclopropanes and stereochemistry next time.